We come to the Earth, which, well, grew to get here, the way it is now. Here is our world, our planet Earth, floating in space. We will be going backward in time, imperfectly, but done in a very disciplined manner. Please notice there is no subduction, no rotation of tectonic plates, no twisting, no form-fitting, no altering shapes or sizes. It would be impossible for these continental plates to fit together perfectly without this being true, and yet the upper tectonic plates fit together perfectly on a much smaller planet. Yes, there's been some erosion, landslides, blah blah, but overall this activity is insignificant. There is a kind of conspiracy of silence among certain scientists. They know but are not telling you that the upper tectonic plates of Earth also join in the Pacific. Not partially, they join totally. You are asked to believe that the continents swim or drift about willy-nilly, bumping and crashing as if they were on a greased skillet. This is not true. The simple truth is apparently too upsetting to too many apple carts. We're now going forward in time to show how the actual growth of the Earth took place. Imperfect as to details, but the overall is nailed. Antarctica, as you see, has become subtropical. Africa, on a smaller globe, moved way downward under the globe. In fact, for hundreds of millions of years, the bottom of Africa was the South Pole. South America's tail goes under and wraps around the bottom of Africa. Then incredibly, it joins coast with Antarctica. 65 million years ago and more, these continents were joined, and marsupials like the duck-billed platypus roamed from Australia, Antarctica, and across southern South America and up into Africa. The platypus. Dinosaurs roamed all over this world on the upper tectonic plate because there were no oceans, just shallow seas. Here today, Antarctica is frozen over, and Australia and its surrounding islands are the remaining home of marsupials. Do you see how broadly the Pacific is opening compared to the Atlantic? This is exactly why the knee-jerk Pangea theory exists. The Pacific spread is too difficult to easily visualize because it's so big. The Atlantic spread is so obvious that a child would recognize it, but they are the same. Check this map out. The Navy and others took core samples to find the ages of the sea bottom. Lo and behold, no part of the undersea was found to be much older than 70 million years old. Does that shock you? It should. It shocked the scientists. Where did they get ancient fish fossils from? From the land, like in Mississippi and Utah and France and China. Most of the undersea wasn't there 70 or 80 million years ago. The measurements of the core samples give the age of the sea floor. Newest, 10 million or so, is red. As we go back in time, we go backward in our rainbow, orange, yellow, green, blue, okay? So we bury the new sea floor back to the fault lines as dictated by color or age. 10 million years back, these are the ages of the seafloor as measured by science, and they're generally true. Earth grew. 20 million? I'm not making this information up. This map comes from the scientific community. 30 million. You can find the same map in many places on the internet. It's common knowledge. 40. The ocean bottom is from 1 year to 180 million years old. 50. 70% of it is no older than 60 million years old. 60. The upper plate, the continents, are as old as 2 billion years old and more. 70. 10 to 20 times as old as the undersea plates. The undersea plate is new and spreading at the rifts. Why does the scientific community desperately cling to and promote the idea that the ocean bottom is sliding under the continents and into a magma which is twice as dense as solid granite? A totally unsupportable and scientifically unsound idea? They have to. Or else they'd have to observe and admit that the Earth is growing. And that, viewers, is a very big deal. That would change everything in science, from the smallest particle to the whole universe. 100 years of scientific theory out the window. That's a lot to give up. It's important to remember that science and the universe should and must be easier to understand as we go back in the universe's evolution. This is an undersea map. As a kind of test for ourselves, we deemed it important to show that not only the upper plate had to fit properly together, but the undersea had to spread in a logical, reasonable pattern that we could see and understand as rational humans. Do you see those lines in the undersea which, beyond information, show direction? The direction of movement apart and away from the rifts. In fact, it's like a movement diagram, isn't it? We're moving now. Let me point out that the newer undersea near the rifts is smoother and more regular than the older land further away from the rifts. Here in the Atlantic, the rift goes right up the middle. Half of the Earth's growth has happened since the extinction of dinosaurs. This means that the Earth is accelerating in its growth. In the last 65 million years, Earth nearly doubled in size. The last redoubling took 600 million years, at least. We're continuing all the indicated undersea directions like following a blueprint. The Earth guides us. And now the land masses will come together perfectly. As we now go forward in time from 185 million years ago, please notice there is no subduction, no raising and lowering of land masses. There can't be. It's hell in the form of magma down there. Local raising and lowering, yes, but not on a massive basis. It can't happen. There's no turning, rotating of land masses. The land masses sit in their individual plates and don't move. The rifts open, that's all. For examination, I'm going to run a few vignettes of each area of Earth that you have a right to be curious about. The North Pole. Man, I love this map so much. There was a piece in the recent National Geo. It shows that the trees in Asia and North America were exactly the same trees. Well, this is why. The land was together when the trees evolved. The South Pole. The oceans have absolutely nothing to do with tectonic spreading, except that they cool the thickening mantle. Tectonic spreading, even according to the most conservative scientists, has created 2/3 of the Earth's surface in the last 200 million years. And therefore, the same must be true on all planets, including Mars. Must. And we can see the younger spreads on Mars just as on Earth. But there is, just as clearly, no subduction on Mars. It can't be both ways. You either have spreading and subduction, or you have only spreading, and you must have spreading. Or you can continue to ignore the facts and say, as the ancients said, that the Earth is unique and singular in the universe, and that we are the center, and the universe rotates around the Earth.
Earth is the only planet in our solar system not to be named after the mythical god. Earth is the densest planet in our solar system. Earth is gradually slowing down. Every few years, an extra second is added to make up for lost time. Earth is almost 5 billion years old. The life resembling today has existed on Earth for less 200 million years. For every species ever lived on Earth, 99.9 are extinct. Despite being called Earth, only 29% of surface is actually Earth. 70% of our planet is covered by ocean, but humans only explore 5% of it. Earth's magnetic pole is moving northward at rate 9 miles per year.
Hi, I'm back at Lakeside School and I'm in the chemistry lab, as you can see. Now, look around you and try and count how many different sorts of materials you can see. 10 easily, 100 not too hard. And if you counted really carefully, well, look at all these materials here. You could probably come up quite easily to 1,000, 10,000 or maybe even 100,000. That's because in a universe with 100 elements, you haven't just got 100 different materials. Those elements can combine with each other in a huge number of different ways to form millions and millions of new materials, all the materials we see in the world around us. All these new materials eventually combine to create entirely new astronomical bodies. The most important by far for us, of course, is our home planet, the Earth. But before we describe how the Earth and the other planets of the solar system was created, there's a little problem we have to take up. You'll remember from the last unit, we saw that all those new elements that were created made up only 2% of all the atoms in the universe. Yet if we look at our Earth, we'll find that 90% of the Earth is made up of elements like iron, oxygen, silicon, magnesium, and other elements created in supernovae and dying stars. So how did they get concentrated like this to form planets and bodies like that? Now, before I give my answer, I'd like to ask if you have any ideas about how that might have happened. To answer these questions, we must think about chemistry. Now, chemistry is all about how different elements link up, how their atoms link up to form what we call molecules. How atoms link up depends very much on the arrangement of their electrons. Some elements, such as helium, are very, very stable. They hardly ever link up with other atoms. In fact, they're known as the noble gases. It's as if they're too snooty to join up with other atoms. You'll find them on the right side of the periodic table, by the way. But most atoms really like to link up with other atoms. We say they're reactive. Hydrogen and oxygen, for example, are always looking for chances to link up with other atoms. If you see burning or you see a flame, what you're really seeing is oxygen linking up really violently with other atoms. It's very reactive indeed. Now, when atoms join together, we call them molecules. Each molecule has its own distinctive qualities, which may be very different from the elements of which they're formed. For example, hydrogen and oxygen are both gases, but when they combine, they form a very, very familiar liquid, water, H2O. And water has qualities completely different from both hydrogen and oxygen. Different types of molecules also have different types of bonds. Some bonds are extremely rigid, but others are very flexible. Some are very strong, very hard to break. Others are very easy to break. So there's a huge variety of different types of links between molecules. Carbon, for example, can link up with itself to form diamonds. Now, in a diamond, the bonds are extremely strong and extremely rigid, so a diamond is very tough indeed. But carbon atoms could also link up with themselves to form a very different material, graphite. Now, graphite is the lead in a pencil. It's very soft stuff indeed. So different bonds make a lot of difference. Now, these different types of links, different types of bonds, mean we have a huge variety of different types of materials. That's what explains the huge variety of these materials. But note that it's mostly elements other than hydrogen or helium that make up these chemicals. And that's one reason why when we talk about rich chemistry, we're talking mostly about that tiny 2% of elements from the periodic table. Atoms began to form molecules even in deep space, in the clouds of matter ejected by supernovae and dying stars. How do we know this? Well, using spectroscopes, we can tell what elements and what chemicals are out there. And we know there's water, plenty of ice, carbon dioxide, ammonia, acetic acid, a whole range of simple molecules that are very familiar in daily life. There are also lots of silicates. Silicates are molecules made from silicon and oxygen, and they make up most of the rocks in the Earth's crust. Now in space, these molecules, which were pretty simple by the way, they included 10 to 20 atoms, at most 60. In space, these molecules couldn't do a huge amount of interesting stuff. But around newly born stars, it turns out you could do a huge amount of interesting stuff with these molecules. In fact, you could make planets. To see how this works, what we're going to do is we're going to travel back in time 4.5 billion years, and we're going to zoom in. We've been looking at the universe so far in this course. We're going to zoom in on one rather average galaxy, the Milky Way. We're going to zoom in on one tiny part of it, and we're going to look at the birth of our solar system. Now, our sun formed like any other star from the collapse of a cloud of matter under the pressure of gravity. That collapse, like many others, was probably triggered by a huge supernova explosion somewhere in our region of the Milky Way. And that supernova explosion also seeded this cloud with lots of new materials from other supernovae and from dying stars. As the cloud collapsed, it began to spin, like a spinning pizza dough. And as it spun, it slowly flattened out to form a disk. Now, this is something that happens throughout the universe, which is why the universe is full of flat disks, from the Milky Way itself to our solar system, even to the rings around Saturn. Astronomers call this sort of disk a protoplanetary disk, or a proplid. Now, as the proplid that eventually formed our solar system began to collapse, at its center it got hotter and hotter and hotter until eventually fusion began and our sun was born. About 99% of all the material in the proplid went into the sun. 99.9% in fact. That leaves 0.1% for the rest of the solar system. All that stuff was orbiting around the sun, and amazingly that tiny residue is what formed all the rest of the solar system. Now let's begin by looking at the outer gassy planets and how they were formed. The intense heat of the young sun drove away gassy materials from the inner parts of the solar system, and above all, it drove away a lot of hydrogen and helium, leaving that as a region deprived of hydrogen and helium. And all that gassy material gathered further out in the solar system and eventually condensed to form the gassy giants. They are Jupiter, Saturn, Uranus, and Neptune. Now, they contained about 99% of the leftovers. So what we're left with is a tiny residue of a tiny residue to form the inner rocky planets, including our Earth. Closer to the Sun, from that tiny residue of a residue, you find material orbiting in the inner orbits. And that material is less gassy, there's more sort of solid stuff. You have little dust motes that eventually will gather together through electrostatic forces or collisions to form little rocks. You have particles of ice that will eventually form snowball-like objects, and then eventually they form things like meteorites or asteroids, and they're getting bigger and bigger and bigger, and they're colliding with each other. And in each orbit, you eventually get large objects that finally sweep up through their gravitational pull everything else that's in the orbit. And so eventually, over 100 million years, in each orbit, you have a rocky planet. Now this process is called accretion. It's extremely violent. There's a huge amount of space stuff smashing into other space stuff. And if you want to be persuaded how violent it was, get out a pair of binoculars and look at the moon one night and look at those craters. Those are evidence of how violent the process of accretion was. our moon was probably created when an object, perhaps the size of Mars, collided with our Earth, our young Earth, and it gouged out a huge chunk of the Earth. And that stuff orbited around the Earth and slowly accreted to form the object that we call the moon. So in this way, through these processes, over about 10 to 20 million years, our solar system formed. And we end up with a solar system that has inner rocky planets in the inner orbits, these large gassy planets in the outer orbits, and woven through them lots of space debris. It includes meteorites, asteroids, and comets. No one knew if there were any other solar systems anywhere else in the universe. It was quite possible this was the only solar system in the universe. But in the last 15 years, there's been some quite magical astronomical research, a lot of it based on satellite telescopes, such as the Kepler satellite. And what we now are able to do is actually see other solar systems. They vary hugely. But we now know that solar systems are actually very, very common indeed. And strangely, what that does is it rather increases the chances that out there somewhere there is life of some form. So exciting is the science, by the way, that I even have an app on my phone that tells me all about the most recent discoveries of so-called exoplanets, which is what planets around other stars are called. Let's return to the problem we began with in this unit. How is it possible from all these rare new chemical elements to create entirely new things? And I hope by now we have the beginnings of an answer. First, we saw that chemistry links chemicals to form simple molecules, a whole range of new materials. They're floating through space. And secondly, we saw that in the environments, and we can call them the Goldilocks environments, around newly formed stars, those molecules get smashed together. They get brought together by chemistry and by gravity and by electricity to form objects like dust motes, meteorites, asteroids, and eventually planets and solar systems. Now, we regard the creation of solar systems as the fourth great threshold in this course. And that's because planets, and in particular rocky planets like our Earth, are significantly more complex than stars. They are more complex because they have more internal structure, but they are also much more complex chemically. They contain a much greater diversity of materials. Okay, now I've worn this lab coat throughout the whole lecture, even though I'm a historian. I think it's time to take it off. But I hope you're beginning to see that what's happening is that our universe is getting more complex, more diverse, and more interesting.